So let's go through the zeroing process. First thing, I just got a drill here. I need to change that drill. So I'll show you how to change tools, and then once we have the appropriate tool in here, we'll show you how to zero that, and away we'll go. I'm going to bring this down just a bit for convenience. Changing the tool, there's a latch on the side here. Unlatch it, open it up. This has a pair of flats, and there's this arm here that will engage those flats. That keeps it from turning. Now I can loosen up the lock rod. If I knew where the wrench was, there it is. One thing, when this comes loose, depending on how tight it was, the last person that tightened it, if it's not real tight, as soon as you loosen this can fall out. When this falls out, it's going to land on something. You can chip the tool, you can dent my surface. Neither one is good. So one hand on this, the lock is engaged. I will loosen it up a bit. Now in this case it's holding okay, so I will take my screwdriver, give it a tap, and I should have been holding it better because I bounced it off my aluminum there, but that's the way to get it out. Too busy talking and not thinking. Okay, so that's getting the tool out. And what this tool goes into, let me just open this up here, okay? I'll unscrew this. There is a collet in here. And the collet has a taper, and as you draw that in through this threaded hole right there, when you tighten that nut on the top, as you draw that in, it compresses that collet and squeezes in on the tool, whatever tool it is. And for these tools, the tool just slides in there. It's got a surface here that will butt against the bottom of the spindle, so I know the precision location. So that holds the tools. Another way to put tools in here would be use the appropriate collet with the right size hole for the particular tool. And there's an assortment of collets around that we can do that with. And this also has slots so it doesn't turn. So as I put it up in here, I'll spin around, find that slot, I can push it up, tighten the nut, but I can take my tool goes in, I hold it up tight, tighten this down, it's good and tight. Now the tool is locked into position. I can flip this out of the, well, if I fail to flip that out of the way, when I go to close it, it doesn't close properly. If you get to that point, don't force it, duh, right? Something's wrong. If something isn't working, stop and think. So what we need to do is just move that out of the way. Now it closes nicely. Here, I can latch that, okay? One thing while I have this open. There are two pulleys here, and there's a sticker up here which you can't see in the camera now. There's a high-speed range that runs with this up here. You command speeds from 250 to 5140 RPM. If I need to change it, I can flip this lever down, flip that down, loosen that bolt. I got slack on the pulley. I can, put the belt on the other set of pulleys, and it's easier without a wrench in my hand. Tighten it up, tighten that up, and that would put me in the low speed range, which runs from 100 to 2,000 RPM, but for now I'm going to leave it in the high speed range. Turn things the right way and flip those handles up, and we're good. Okay. So now I've got the tool that I need. The machine is referenced, so the machine knows where it is. What I need to do now is find where this part is in reference to the machine. So what I'm going to do, I've measured the diameter of my cutter here. And if I move it down so it's just touching the edge, I know that the axis of the spindle is 1/2 cutter diameter away from this edge. So and then I know where the edge is. Okay? And we're not going to just jam it into the edge. Helps if I go the right way. Come over near the corner where I want to measure, and I'm going to take a Lifesavers wrapper because I happen to know that this is 1/1000th of an inch thick, and I can put it in here as a feeler gauge, and then as this gets close enough to touch, when this gets close enough to touch, I'll be able to feel that as I wiggle this, and then that'll tell me that I'm 1/1000th away from touching. So I can move this fairly quickly in to get close. Now that I'm close, I'm going to use my pendant here and I'm going to click on the X button, set in the X direction. I'm going to move it slowly, slowly, slowly. Now I'm getting real close. Now I'm going to use the jogger, just move it one step at a time. You can hear it clicking. Each one of those steps is 1/2 thousandths. And I'm wiggling the cellophane, and at some point you should get, it's touching. I can feel the drag. If I go one more step, 2 more steps. Well, now it stays there by itself, I think. Barely. There it is. Okay. I must have. It's now just tight. I can't get it back in here. Okay. So that was just touching. So now this cutter is 1/1000th of an inch away from that surface. The diameter of my cutter is 0.1875, and I just highlighted this readout here, and I'll hit enter, and now it's set that as a position of the cutter in the x-axis. Okay, these fields here on the screen tell me the position x-axis, y-axis, z-axis, and they're relative to wherever I've set an offset. These are called digital readouts. Back in the olden days when you didn't use a computer screen, you would really have, well, not the olden days, the medium days, you would have digital readouts up above your machine. In the olden days, everything was done with graduations on a dial, but people still refer these as digital readouts or DROs. If you read the manual for this, they'll use the abbreviation DRO everywhere, and it just means digital readout, and it just really means a field on this screen that you can type something in. So anyhow, I know where I am in the X. I'm going to go up to clear my part. Now I can find Y using a very similar process. I'll move this over. Back down. And I want to make sure that I've got this turned so that I'm feeling the edge of the flute and not in a valley. Put my cellophane in there. I move it in fairly quickly, start, and then I'll move it slowly with the pendant. I'm getting close. Okay, now it's tight. I just touched. So I'm going to back it out a little bit. If I touch it going slowly, we're okay. If I bring it into the part, going full speed, I'm damaging things, and that's not what I want to do. So I'm going to step it in here, and there it is. It's just now tight. So that is minus 0.1875, right? to add that 1/1000th for the cellophane. Enter. And I forgot to do that extra thousandths when I was on the other axis, but that's not important because it's just a random piece of scrap and we're just putting a hole in a random place, okay? So now I got the part, I've got it mounted into the machine, it's mounted flat, it's mounted square. I found this corner. If I bring the page up so it clears, and I can type commands in here. I want to x0, 0, y, 0, send it to the 0, 0 position, and it's moving at the feed rate that whatever the last feed rate we used for anything was, because we'll talk about that in a minute. So I have this, the center of this cutter should be exactly centered on that corner, okay? And it looks pretty close. It's always a good double check. If I knew the exact dimensions of my piece of metal, I could go back to this side over here. Hang on. And I could bring it down and touch it off using the same process, and I could compare the result from moving it over with my known part dimension and know that I didn't goof up the first time. That's a good double check, okay? One more dimension to set. Let me give myself a little clearance. I can move it over. Too far. I need to set the height. I could do the same thing with the cellophane, okay? But this cutter is sharp. See that Band-Aid? That cutter is sharp. That's the reason there's a Band-Aid there. It tears the cellophane. It doesn't work as well. So what I'll use is something that has a known diameter, like this rod, which I might. And if I can roll underneath freely, I know I'm above that diameter from the part. If I go down, and I don't roll it down while this is underneath because I don't want to jam it down onto that part. Okay, now this doesn't roll underneath, okay? So I know I've gone too far down for that distance. I can use my pendant, click on the Z, I'll send it in the plus direction till this rolls. I don't mind wiggling it while it's going up, I just don't want to be doing that while it's going down. Now I'm just above, and I always like to set this distance going down because there is a couple thousandths of hysteresis, so I'm going to down just a little bit, and now I'm going to bring it down a few thousandths. And just keep trying to roll it underneath. Get my hand out of your way. But now I'm touching that flute over there. Some of it might be, it's touching, it's barely. You know, obviously you don't want any chips or anything on the surface. Now it definitely doesn't go down. Now I can tick, tick, tick. Now it goes underneath. It's just, I can just feel it touch as it goes past these. So now that was going up. I'm going to go up a couple more. The thing is, because this is a stepper motor and not a commanded thing, every time I click it, it does a command, but any backlash or hysteresis in the ball screw mechanism means there's lost motion. So that was going up. So I'm just, let me go one more up. Okay, so now I'm going, I can just go underneath. I can click it down one, and it still goes underneath just about the same. Another one, another one. So there's just a couple, like a thousandth or less of hysteresis. But the bottom line is I like to find this touching point as I'm moving down, so if there is any hysteresis in this, it's accounted for, because when I'm drilling, I'm going to be going down. So, and it's just, I can just feel it, just nicking as it goes past. So what I will type into the z-axis here is the full diameter of this, obviously. That is 0.4196. enter, and I don't have any cellophane, so I don't have to allow for anything like that. So now I know where my part is in the X direction, the Y direction, and the Z direction, and now we're actually to a point we can start thinking about making chips. Okay? You ready? 3, 2, 1, go. Okay, welcome back. So at this point we've talked a little bit about safety. I will remind you there's no more important safety device than what you got between your ears. You know, you got something there, let's use it. If something doesn't feel safe, then it's probably not, so don't do it. We've got the part in the machine, we've got the machine zeroed, we know where our corner is, we've found our axes. I've got this very corner of the part set to be 0, 0, 0 in terms of the top corner there. So given all that, we're actually in a position we can start thinking about making a part. So what are we going to do? Well, there's a lot of different ways we can do this. We can move the machine manually, just like I was using with the keyboard and the pendant, and move it around manually and machine things manually. We can draw a part in SolidWorks or AutoCAD or CATIA or anything like that and come up with a surface drawing, and then we can put it in a tool like EdgeCam. EdgeCam will create the tool paths around that surface that we need and finally create the code that we need for this machine here. Or for this example, since we're just kind of showing you how things work, this machine does have a lot of what they call wizards. And I click wizards, pick wizard, and I'm going to go down here to rectangular pocket. So basically it's just a recessed pocket, rectangular in shape. And I can specify a number of things here. Let's walk through them. I got a width and a length. So the width is in the y-axis, front to back. Here it's 1 inch. Length is 2 inches. I could make this 2.5 inches. Let me retype that. 2.5. And I have to hit enter for it to stick. If I just type it and move on, it doesn't stick in these things. So now I'm going to create a pocket 1 inch by 2.5 inches. The position of this pocket, I've got an X and a Y position for the center of the pocket. I can put the X position at 3 inches, and now it's going to, the center of that pocket is going to be 3 inches over from this edge. In the Y direction I have it at 1.5, so it'll be in 1.5, so it's going to center that pocket about the point 3 inches in the X, 1.5 in the Y from that very corner. Those are here and here. I've got a rough feed rate. This is in, because we're in inch units, it's in inches per minute. It's set at 10 inches per minute, which is okay for aluminum. And you know, I don't like to push this machine too hard. Finish amount is 0.1, so it will get within 1/10 of an inch and then make another pass to do a finish pass, and it'll do it at a finish feed rate of 5 feet per minute. So it'll go rough it out quickly, then slow down and finish it off slowly at 5 inches per minute. Percent step over. If this is my cutter and I make a pass, I'll cut a slot this wide, right? And then when I move it over, if I move it over 100%, then I'm going to cut a slot right next to it. If I move it over 50%, the cutter will be overlapping by half. So you want some overlapping so you don't potentially get a ridge or something. Here it's set at 60%. We'll live with that. Rapid height. What is a rapid height? There are times when this machine is going to move quickly in an XY direction, and we want the cutter to be clear of the surface so it doesn't impact anything. Here it's set to 1/10 of an inch. So looking over here at the part, you know, so before it moves quickly, it'll raise the cutter 1/10 of an inch above our Z plane, which is the top surface, move quickly, and then go down. And that's safe because this is a flat piece. Let's suppose instead I had a part held down with a toe clamp, okay? and I drilled a hole here, and I want to move over there, a toe point back here. If I raise the cutter 1/10 of an inch and rapidly traverse across my part, I'm going to crash into the clamp. Okay? So if I've got clamps and things going on, I have to have that safe Z height up above the thickness of this toe clamp. You want it up a good inch or so, maybe even 1.5 inches, so that it comes up, clears everything, and then goes back down. Okay? So be aware of obstacles and things going on in your mounting that you could crash into with the cutter. Other things on the screen. Feed plunge, that's 3 inches per minute. That's how fast the cutter is going to go down into the material. It's going to go down a step depth of 0.06 inches or 60 thousandths of an inch per each time it goes down. It's going to go down another 60 thousandths. The total depth of this pocket is 100 thousandths or 1/10 of an inch. I'm setting my spindle speed at 1500 RPM. Inches are units. It's spinning clockwise. And here I'm turning the coolant on because when I'm machining aluminum, I like to have the coolant going because cutters tend to clog up, and with the coolant it flushes the chips away and keeps the cutter from clogging up. So that's all the parameters I've set. One more up here, there's climb mill and conventional mill. If imagine, and it's probably easier to imagine this way, if my cutter is turning this way, if I'm machining along like this, the cutter wants to climb up on top of my surface, okay? It's going to kind of pull the cutter into the material or pull the material under the cutter. I don't know if my fat fingers are in the way. I'll do it this way. So if I'm turning this way, this is climb milling where it's pulling into the surface. Conventional milling, your cutter's rotating this way and you have to push the cutter into the material and it's less likely to grab and pull. So typically we prefer to do conventional milling as opposed to climb milling just because you're less likely to grab and pull the material in. That's everything on this wizard. There's a whole bunch of different wizards in the machine. They're all different, and the terminology is different. They're written by different people. So just make sure you understand what every single entry is on here. Don't say, well, I don't understand it, it's not important, because you may find that in fact rapid height, what's that, who cares? Well, if the default is fine, but had there been toe clamps in the way, you would have been breaking bits. So we post the code. We have the option to save the settings so that we come back to the same thing next time. We don't need to. Exit. And we now have code in our window here, and we'll get to that in a minute. And I also have a drawing here, the dark blue. I don't know if you can really see it. Let me go to a different window. Go to the toolpath window. It blows it up a little bit. But this shows our the position of our cutter right now is at 0, 0, and the path it's going to take to get to the start of the cut, and then the cutting path it's going to take as it goes around and around. And I can take this drawing and I can rotate it to look at it from different angles. And if I get to this angle, it's probably almost impossible to see on the video, but you can see the different depths. So I can play with that, look at the tool paths. Okay? Most of the time I just use the simple run screen right here. So there's the paths that the tool is going to take, and here's the code. If this is the first time you've run this wizard, or the first time you've gotten code from somebody, there's a lot of things that can go wrong in this code. So we've got some code that's been created, and we're going to take a look at it because sometimes you really do need to look at this code. So if I click on Gcode, change Gcode, it brings it up in a text editor. And the Gcode or NC code or Go codes or whatever you want to call it, this stuff has been around since the late 50s, early 60s. So it's not, it's not your nice, object-oriented, fancy stuff. It's pretty primitive stuff that was originally written for pretty primitive processors. and basically it's just a set of alphanumeric codes. Each code translates to a specific machine action. And one of the things that this code will do, the way, for example, G0 means a rapid transit. G1 means you're going to do a transit at a fixed feed rate. Every time you move the cutter, you don't want to have to keep typing in the same feed rate over and over. You don't want to have to type, G1 every single time. It'd be nice just to be able to type in the coordinates and have it go there. So the way this code works is once you type something in, like a G0, a G1, to move fast, move slow, every movement is going to move at that previously specified rate. Every time you put in a command to tell it to do something, it doesn't forget those commands and they stay in place. So considering that the last person who used this machine could have commanded things like put it in metric mode or commanded real high movement rates or something, the first thing we do in our Gcode is a safety block. And I don't know how close you want to zoom in. Can you? Okay. This is great here. I've actually got a person operating the camera. I should make you come around and say hi. It'll only be half as boring. Each of these codes is basically to get things set up and undo things that previous people might have done. So you've got a G0, so initially any movement we make is going to be fast. A G49 turns off any tool offsets that might have been applied. Excuse me. A G40 turns off any cutter radius compensation that somebody might have applied in a previous program. G17 is selecting the normal XY plane. G80, what is G80? Oh, Cancycle. Yes, that's an important one. Let's talk about Cancycles for just a moment. If I'm drilling a series of holes in a plate, okay, I don't want to have to, and suppose I want to do what's called a PEX cycle. In a PEX cycle, you drill down, you pull it out to clear chips, you drill down a little further, you pull it out to clear chips, drill down, pull out. Okay, if I had to program that cycle manually, it'd take a lot of steps, a lot of codes, each movement down, each movement up at a different rate, movement down at a different rate, up, down, up, down. But they provided for what they call Cancycles, where I can just tell it I have a PEX cycle, I've got a final depth, I've got the clearance that I want to pull out to after each pull out and things like that. And once I turn that Cancycle on, every time the part moves to a point, it just sits there and does the drill. I pull it out, it moves, it does drills the hole, moves, drills the hole. So I can drill a dozen holes without having to keep repeating the same Gcode over and over. I have this Cancycle active, so I just have it move to a point and it all happens automatically. Well, if the previous person who was using the machine had a Cancycle active, when I go to do my pocket, I'm going to tell it to move to some XY point, and if the Cancycle was still active, it'd try to jam that cutter down like it was a drill and drill a hole. We don't want that. So G80 turns off that Cancycle. G50 turns off the any scale factors. I could apply a scale factor to stretch and distort my part if I want, but normally I don't, so we turn that off. G90, what was G90? Oh, G90 says you're in the absolute mode in terms of positioning. There's absolute and incremental mode. In absolute mode, I tell it to go to 0.33, which will be 3x, 3y from my 0 point that I set. In incremental mode, I could tell it to move x a tenth of an inch, y a tenth of an inch, x a tenth, and things like that, where I'm making an incremental move from wherever I happen to be. But this code is written in absolute mode, so we turn the incremental, set it to absolute mode. Next line, M6 is a spindle command. No, M6 is tool change, I'm sorry. Yes, M6 is tool change, so it's saying change to tool 0, T0. I don't have an automatic tool changer on this machine at the moment, so basically it's going to stop the program and say, put tool 0 in. and it's the comment, the stuff here in parentheses are comments. For this auto-generated code, there's not a lot of comments. If you're ever writing Gcode on your own, please be liberal with the comments. It makes life so much simpler. Next line, G64. I don't remember what that one is. Each constant velocity mode, that's just the way the machine moves, versus stopping at each corner and restarting. G20 tells it's in inch mode, and I just wrote on the screen. Okay. G20 puts it in the normal inch mode. This is important, right? If the previous person had been working, well, let's say the previous person had been working in metric or inches, and we wanted to do this in metric, we give it all metric dimensions. You know, so I'm going to tell it to move 100 millimeters. Well, if the previous person had been in inch mode, the machine is going to interpret it as 100 inches, right? And it's just going to go charging off until it crashes into something. So you need either the G20 or the G21 to make sure that you have it in the correct mode, inches or metric. Because again, it remembers from the last person. Once you tell it it's in inches mode, it stays inches mode until told otherwise. M3 is a spindle command. It's telling it to run the spindle at 1500 RPM. M8 turns the coolant on. G00, G0, or G00, does the same thing, is a rapid movement. G43 applies any tool length offsets that may exist for the tools. The H is the tool offset, it's 0, so we're just applying a tool offset of 0. And the Z0.1 is basically we're setting the tool offset to 0 and rapidly moving to a height of plus 0.1 inches. So it's going to move till the cutter is 1/10 of an inch above my top plane reference surface. G00 is going to move rapidly to the X 2.25, Y 1.5, so it's going to move rapidly to the middle of my pocket approximately. And then it's going to do a G01, which is a move at a fixed feed rate, a linear move. Z is going to go down minus 0.06 inches at F3, a feed rate of 3 inches per minute. And then it's going to move from the point that it's going to move in the X direction to X 3.75 at a feed rate of 10, the F10, okay? So you can read through this and see that everything's turned off that should have turned off. It's in inch mode, not metric, so you didn't, you could have made a mistake and left metric, clicked when you wanted inches. Potentials for disaster is enormous. So you kind of want to go through this code. You don't have to look at every single, Y 1.2825, X 2.0325, blah, blah, blah. You don't have to look at all these moves. I would look at them, just scan through, and they're all on the order of 1.7, 0.96, 0.32. They're in a range that I would expect to be reasonable for this area here on this surface. If I saw X equals 10, that's off the edge of my part. That's crazy. Something went wrong. Okay, so you may just scan the magnitude of the numbers. You don't have to look at every single move. And then when we get down to the bottom, we see that we get we got a rapid movement to plus 1/10 of an inch. M5 and M9 stop the spindle, shut off the coolant. M30 stops the program and rewinds it. It's worth looking at the very end. What I've seen in some programs is it will move to Z00, and then it'll command a rapid move back to XY00 or to some XY coordinate. Well, if you're making that rapid traverse with the Z set to 0, basically you're raking the tool across the top of your part, right? In this case, we machined out a pocket, so it wouldn't be touching, but in other parts, that's not necessarily the case. So make sure that you don't do some rapid XY movement without first retracting the spindle. I won't say what program it was that had a tendency to do that, but it could have very well been an older version of Mastercam that I didn't say. And that problem has since been fixed, but it's something that showed up regularly. Okay, so that's our whole code run through, it's worth the run through. Click OK, so there's the tools there. And now we're essentially ready to start making chips. I mean, there's a lot of other, factors in machining, and, obviously I have not given you enough information to be an expert machinist, because I'm not an expert machinist myself. I'm an engineer and an edumacator, I hope. But I won't, give you the feel